Welcome to this video on fiber optic communication. In this video, we will be discussing on one of the optical sources, the LED, that is light emitting diode. We will be looking into the choice of materials for LED, the principle of operation and the various LED configurations and the calculation of quantum efficiency for an LED. The two types of optical sources are LED, that is light emitting diode, and laser, light amplification by stimulated emission of radiation. We shall compare an LED versus laser. LED, the transition of an electron from the conduction band to the valence band is spontaneous. Therefore, the emission of a photon or light is spontaneous. Whereas in a laser, the electron transition from the conduction band is stimulated. So, it is stimulated emission and amplification. LED is an incoherent source, whereas laser is a coherent source. That is, the light is of the same frequency and a constant phase difference is maintained. For LED, no optical resonators are used, whereas in laser, optical cavity resonators are used for light amplification and wavelength selectivity. The beam width for the light emitted by an LED is large, whereas it is narrow in the case of a laser. The spectral width of LED is broad, that is, the range of frequencies over which light is emitted is broad in LED and it is narrow for a laser. The modulation rate of an LED is around 100 Mbps and it can go up to 10 Gbps for a laser. The coupling efficiency is less for an LED and higher for that of a laser. An LED can be used only with multimode fibers since the coupling efficiency is low and the large beam width, whereas laser can be used for both single mode and multimode fibers. The major advantage of an LED is that it has low temperature dependence and longer lifetime, whereas laser has high dependence on temperature and the lifetime is lesser comparatively. Let us look into the operation of a PN junction diode. PN junction is made up of P-type material and N-type semiconductor material. The N-type material, which is made of pentavalent or group 5 elements, has a majority carriers as electrons, and the P-type material, which is made of the group 3 or trivalent elements, it has holes as the majority carriers. And the junction that is formed between the PN junction, it is depleted of charge carriers and it is called the depletion region. So, when a PN junction diode is forward biased and when the voltage is greater than the potential barrier, then electrons flow from the N-type region semiconductor to the P-type region and recombination of electrons and holes, that is recombination of charge carriers takes place. So, the flow of current is given by the recombination can be of two types, radiative recombination and non-radiative recombination. In the case of radiative recombination, the excess energy is emitted as photons, whereas non-radiative recombination, the excess energy is emitted as one or more phonons or transverse kinetic energy. So, the picture on the right hand side gives the various types of carrier recombination. First, for a direct band to band recombination, the probability of emission of photon is high. So, it is a radiative recombination. The Schottky Reed Hall recombination and the Auger recombination are non-radiative recombinations. In Schottky Reed Hall recombination, intermediate level is present due to crystal defects or foreign atoms. So, here recombination centers or traps are established. So, when these centers are closer to one of the band gaps, then recombination probability is lesser, but when it is midway between the two, recombination possibility is higher, but the energy is less and therefore, the excess energy is released as phonons or vibrations. In the case of Auger recombination, three carriers are involved, the electron and a hole that recombine, and the excess energy is transferred to an electron in the conduction band which moves to a higher state in the conduction band. And later when it falls down to the lower state in the conduction band, the excess energy is released as thermal energy. So, Band to band recombination, which is direct recombination, is radiative, and the other two recombinations are non-radiative. Now we shall see what type of materials result in radiative recombination and what in non-radiative recombinations. So when electron transition from or to the conduction band occurs, that is with emission or absorption of photons, both energy and momentum must be conserved. So in direct bandgap materials, the maximum energy of the valence band and the minimum of the conduction band occur at the same momentum, and therefore when the electron transition occurs, the difference in energy is emitted as photon. The probability of radiative recombination is higher in the case of direct bandgap materials. In indirect bandgap materials, the maximum energy level of the valence band and the minimum of the conduction band, they occur at different momentums. Therefore, a third particle called the phonon is required for conservation of momentum. There is either absorption of phonon or emission of phonon before the recombination occurs. Therefore, the possibility of radiative recombination is lesser. So, as was discussed, in a direct bandgap material, the maximum and minimum energy levels are at the same momentum and the recombination occurs with release of photon. Whereas in indirect bandgap materials, the energy levels occur at different momentum and phonon is required to conserve momentum. So, this results in slower recombination and longer minority carrier lifetime and greater probability of non-radiative recombination. So, for choosing a material as an optical source, direct bandgap materials should be chosen. Only then they will emit photons. And also for the semiconductor device fabrication, materials with similar lattice structure has to be chosen, so that the strain and stress induced due to temperature variations is minimum. This will result in higher efficiency and longer lifetime of the optical source. Coming to LED. So, LED is used in optical communication systems when the bit rate required is lesser than 100 to 200 Mbps and used with multimode fibers. The major advantages of LED are it has less complex driver circuitry because there is no need for optical or thermal compensation, and it is less expensive and the lifetime is longer. LED emits light over a broad spectrum, and spectral slicing, that is, the broad spectrum is split into narrow slices by using passive devices like array waveguide grating. So, using this, LEDs can be used for short distance high data rate transmission and where multiple wavelengths are to be multiplexed into a single fiber. LED can be used for various applications such as lighting purpose and others, but when LED is to be used for optical transmission purpose, it must have the following properties: high radiance output, fast emission response time and high quantum efficiency. Radiance output, that is, radiance is a measure of the light that is emitted from per unit area of the source into a unit solid angle, and this needs to be high, that is, the light emitted from a unit area of the LED into a solid angle should be high, so that coupling of light into the fiber can be efficient. And fast emission response time. Response time is the time delay between application of a current pulse and onset of emission. That is, it determines how fast the output changes with respect to change in the input current that is given to an LED. This determines the data rate that can be supported by the source. And quantum efficiency. This is the amount of photons or the number of photons that are emitted from the LED to the number of recombinations that occur. This should be high so that the radiative recombination is higher. So, to have high radiance output and high quantum efficiency, the LED structure, the charge carriers and the photons should be confined to the active region of the PN junction diode. To achieve this, carrier confinement and optical confinement is required. So, carrier confinement, that is confining the carriers to the active region of the PN junction diode. So, this results in high radiative recombination. So, this will result in high quantum efficiency. And optical confinement, that is confining the photons that are emitted to the active region, this will prevent absorption of the emitted radiation by the surrounding PN junction material. So, high carrier and optical confinement can be obtained by having a double heterostructure or double heterojunction structure. This diagram gives basic double heterojunction structure with gallium aluminum arsenide as an example. The active recombination region is present and it is surrounded by two different alloy layers on either sides. This enables confinement of carriers and confinement of photons. So, X is greater than Y, so that it provides for both optical and carrier confinement. The second diagram shows the band gap difference between the different layers. This enables confining the charge carriers and recombination of them to the active recombination region. And the third diagram shows the variation in refractive indices, which enables confinement of the optical photons that are being generated. So, the refractive index is less for 1 and 5. Therefore, the photons that are emitted are confined to the waveguide region. In addition, the double heterostructure has other parameters that influence the performance of the device, such as self-absorption, that is absorption of the photons by the material itself, carrier recombination at heterostructure interfaces other than the active region, recombination at other interfaces, then doping concentration of active layer, injection carrier density and active layer thickness. Let us look into the two configurations of an LED, the surface emitters and the edge emitters. First, the surface emitters are also called the burous or front emitter. Here, the plane of the active layer that is emitting light is perpendicular to the axis of the fiber. So, we have the active PN junction layer here surrounded by the double heterojunction layer to confine optical and carriers. A circular well is etched in the substrate and the fiber is cemented to it. The light that is emitted is perpendicular to the axis of the fiber, and the circular area is around 50 micrometer in diameter and 2.3 micrometer in thickness, and the emission is isotropic with 120 degree half power beam width. The isotropic pattern is Lambertian, that is, it is equally bright when viewed from any direction with respect to a particular angle, that is cos theta, where theta is angle between the viewing angle and the axis of the fiber. So, when the angle increases, theta increases, the intensity of light decreases, and the intensity is maximum at 60 degree, and therefore, the half power width is at 120 degrees. Next is the edge emitting LED. Here, the emission is along the direction of the fiber axis. As we can see, the active PN junction layer is surrounded by the double heterojunction layers. The emission pattern of an edge emitting LED is more directional compared to that of a surface emitter. So, in the parallel plane, the emission is Lambertian with an angle of 120 degree, and in the perpendicular plane it is 25 degree to 30 degrees. We have seen the choice of materials for a light source should be direct bandgap material, so that the radiative recombination probability is higher. So, binary compounds of group 3 and group 5 elements are used. Examples of group 3 elements are gallium, indium and aluminum, and group 5 elements are phosphorus, arsenic and antimony. And also ternary and quaternary combinations of these binary compounds are used. So, the binary compounds could be aluminum arsenide, gallium arsenide, indium phosphate, so on, and quaternary or ternary combinations of these elements are again used. So, for operation in the 800 to 900 nanometer wavelength range, gallium aluminum arsenide is used, where X indicates the aluminum mole fraction, and it determines the concentration of X or the concentration of aluminum determines the band gap energy and the wavelength of emission of the source. As can be seen in the graph, the various fractions of aluminum mole fraction X determines the band gap energy and the wavelength of operation. For longer wavelengths, that is in the 1000 to 1700 nanometer range, indium gallium arsenide phosphide is used. So, the full width half maximum, that is the width, the spectral width when the intensity of light is half of the maximum value, that gives full width half maximum. So, that is for LED operating at 800 nanometers, it is around 36 nanometers, and for LEDs operating at in the range of 1300 to 1600 nanometers, the spectral width is around 70 to 180 nanometers. As can be seen in the diagram, the spectrum of the surface emitting LED is broader compared to that of the edge emitting LED. This is because of difference in self absorption by the different configurations. So, when materials are chosen for light sources, direct band gap materials are chosen so that the probability of radiative recombination is higher and adequate optical emission is available. Next, we should take care that the lattice parameters of the materials match, so that temperature variations would not cause strain in the heterostructure interfaces. Less strain at the heterostructure interfaces due to temperature variation will result in higher quantum efficiency and longer lifetime of the optical source. Okay, the energy of the light emitted by the source is given by E is equal to h nu, that is equal to hc by lambda, and lambda is 1.24 by Eg, where Eg is the band gap energy in electron volts. So, when choosing materials for the source, materials with the same lattice constants but different band gap energies are chosen, as can be seen for gallium aluminum arsenide and aluminum arsenide, which have the same lattice parameters but different band gap energies are chosen, and it is gallium 1 minus X, aluminum X and arsenide, where X is the aluminum mole fraction which determines the band gap energy and the wavelength of emission of the source, and this band gap energy is given by this expression. And for longer wavelengths, indium gallium arsenide phosphide is chosen. It is actually a quaternary combination of binary elements. The binary elements are indium arsenide, indium phosphate, gallium phosphate and gallium arsenide. Their lattice parameters are different. So, the shaded region gives the matching areas, and when indium phosphate is chosen as a substrate with this point and the materials are grown over indium phosphate such that the lattice parameters match, then the band gap energy is given by this expression. Next, moving on to quantum efficiency of an LED. The efficiency of an LED is the optical light or the number of photons emitted to the total number of recombination of the carriers that take place. So, for calculation, this is divided into two parts, the internal quantum efficiency and the external quantum efficiency. Internal quantum efficiency gives the total number of radiative recombinations that occur to the total number of recombinations. And external quantum efficiency is the total number of photons emitted from the material to the number of photons that are generated. So, we will look into the derivation of the same. So, when a p-n junction is forward biased, excess carriers are generated. So, when there is no carrier generation externally, the carriers that have been generated, they will recombine and the carrier density decays exponentially, given by this expression n is equal to n naught into e power minus t by tau, where tau is the carrier lifetime and n naught is the initial injected excess carrier density. These excess carriers, they recombine either radiatively or non-radiatively. When they combine radiatively, photons are emitted, but when they combine non-radiatively, it could be self-absorption of the energy or it could be carrier recombination at the heterostructure interfaces and not at the active region interface, or it could be an auger process where kinetic energy is released. So, when constant current flows into an LED, the carriers are injected and recombination occurs and neutrality is maintained. That is, rate of change of carrier density with time is equal to rate of carrier generation minus rate at which the carrier density is decaying, given by dN by dt, that is the rate at which the carrier density changes, and the rate of generation of carriers given by J by QD, where J is the current density and Q is the electron charge and D is the thickness of the recombination region, minus the rate of decay of the carrier, where tau I is the carrier recombination rate. At equilibrium, there is no change in the rate of carrier density. Therefore, dN by dt is 0. So, substituting that in the equation, we get N is equal to J tau by QD. So, now let us calculate the internal quantum efficiency. It is defined as the radiative recombination to the total recombination that occurs, and the radiative recombination lifetime is given by tau R and non-radiative recombination lifetime is tau NR. So, the first equation dividing the numerator and denominator by RR, that is radiative recombination rate, and substituting the recombination lifetime, and internal efficiency is given by the bulk recombination lifetime by the radiative recombination lifetime. It has been observed that the internal efficiency is 50% for homojunction LEDs, whereas for double heterojunction structures where their charge carriers are confined to the active region, the internal efficiency improves to 60% to 80%. Now, calculating external quantum efficiency. Radiative recombination results in emission of photons, but all the photons that are generated are not emitted by the material. Some of the photons are absorbed by the material itself. So, external quantum efficiency is the ratio of photons emitted from the LED to the number of photons that are generated internally. As can be seen in the picture, those photons that make an angle lesser than the critical angle are emitted, whereas the others are reflected back into the material itself. So, the external efficiency is given by this expression, where T phi is the Fresnel transmission coefficient, and for simplicity, considering only normal incidence, T of 0 can be approximated to be 4 n1 n2 by n1 plus n2 the whole square. Substituting this value in the expression for external efficiency, we see 2 pi and 2 get cancelled. So, we have 2 n1 n2 by n1 plus n2 square outside, integral of sin phi d phi, and integrating that gives cos phi, and substituting we get an expression, and we see n2, the external medium is air. So, it is equal to 1 for air, therefore, external efficiency is approximately equal to 1 by n1 into n1 plus 1 the whole square, and the power emitted by an LED is given by the external efficiency into internal power, that is power internal by n1 into n1 plus 1 the whole square. So, this is the quantum efficiency of an LED and the total power emitted by an LED. Next, we shall see modulation of an LED with an AC signal, how the LED responds to change in frequency. So, response time or frequency response is determined by how fast the LED responds to AC signal. The frequency response depends on doping level in the active region, the injected carrier lifetime tau I in the recombination region, and the parasitic capacitance at the junctions. So, the optical power with respect to the modulation frequency P of omega is given by this expression, and this modulation bandwidth can be defined either as an optical or electrical bandwidth. But the input to a source or an LED is electrical signal. So, we normally consider modulation bandwidth of the system with respect to electrical terms. So, the modulation bandwidth in terms of electrical signal, it is a point where the electrical signal is half of its constant value, that is the electrical 3 dB output. The electrical ratio is given by 10 log electrical power for a modulating frequency omega by electrical power at 0 modulating frequency, and the current and power relationship is given, power is equal to I square R. So, substituting the value of I. The electrical 3 dB point is where the electrical power has reduced to 50%, and substituting the value of current for it, we get it is equal to 1 by 2, and current, the ratio is 1 by root 2, that is 0.707, which can be seen in this graph. Next, talking of the optical bandwidth, the optical source has a linear power current relationship, that is power is proportional to current. Therefore, the ratio, optical ratio is 10 log optical power for a modulating frequency omega to optical power at 0 modulating frequency, and that can be replaced by the value of current, and taking the 3 dB optical point, it is the point where the power is 50%, and the substituting in terms of current, it is 1 by 2, that is 0.5. So, this gives the optical 3 dB point. So, electrical 3 dB point is where when the y axis is in terms of current, the electrical 3 dB point is where the current ratio falls to 0.707, and the optical 3 dB point is where the current level falls to 50%. In this video, we have discussed on one of the sources for optical transmission systems, that is a LED. We have seen the principle of operation of an LED, the choice of materials for an LED, the configurations, and then the calculation of quantum efficiency, and also the modulation of an LED by AC signals. These are the references used. Thank you.